Hello dear students. Today I am going to discuss question number 7 and question number 8 of the chapter on fluid mechanics. The question number 7 says the rise of liquid of specific gravity gamma in a capillary tube of radius r is given by sigma upon 2r gamma twice sigma upon r twice sigma upon gamma r and gamma sigma upon 2r. So this question is related to the rise and fall of a liquid in a capillary tube. Let us discuss this question in detail. Consider we have a liquid in a container and a capillary tube which is a small diatube having the diameter of about 0.5 millimeters to 2 millimeters. Consider that a capillary tube is immersed in a liquid container we can have two possible scenarios. Either the liquid in this container will rise up this capillary tube or it will experience a fall in the capillary tube from the normal surface level of this liquid in a container. Now this rise or fall of a liquid up the capillary tube depends on the interplay of adhesive and cohesive forces. Cohesion is the intermolecular force within this liquid, and adhesion is the force of attraction between this liquid and the surface in contact. Say in this case, if the water is liquid and the material of the capillary is glass, so the molecules of water experience a force of attraction with the glass surface, and that attraction is known as adhesion. Similarly, the molecules of a liquid exert an attractive force on each other, and this sort of attractive force is known as cohesion. Now, if adhesive forces dominate the cohesive forces, the liquid rises up in the capillary tube. If the adhesive forces are less than the cohesive forces, the liquid falls in the capillary tube. To have a better clarity of this phenomena, let us consider an observation which we encounter on a daily basis. We observe that when certain droplets of liquid fall on a surface, we can see two possible scenarios. The liquid droplets either flush with the surface, that is, this liquid tries to flatten itself over the surface in contact, or it tries to retain its spherical shape when it comes in contact with certain surfaces. If this liquid experiences an attractive force with the surface in contact. The liquid tries to spread itself over the surface in contact. In this case, adhesive forces are dominant over the cohesive forces, that is, the intermolecular forces in this liquid droplet. Now, in this parallel scenario, the intermolecular forces within the liquid droplet dominate the adhesive forces. In this case, the liquid does not flush with the surface. It retains, or it tries to retain, its droplet shape, its spherical shape. While in this case, the liquid wets the surface. So when adhesive forces are greater than the cohesive forces, the liquid wets the surface. And in this case, when the cohesive forces dominate the adhesive forces, the liquid does not wet the surface. Similar kind of a phenomena is played when a liquid tries to rise or fall in a capillary tube. Suppose we have a capillary tube. If the liquid in contact experiences attraction with the walls of the capillary tube, it gets attracted to the tube, and in the process, the liquid rises up. The liquid molecules closer to the surface of the capillary tube experience a force of attraction with the glass surface or the material of the surface of the capillary tube, and therefore in the process of this attraction or adhesion, it rises up. When it rises up, it pulls the adjacent liquid along with it, because the liquids have a property of surface tension. This liquid surface acts as a membrane. When the molecules closer to the surface are attracted to the surface in contact of this capillary material, and in the process they try to spread on this surface, they pull the molecules in the body of the liquid within this capillary tube along with it, and hence a meniscus is formed. Okay. Similarly, if the liquid molecules experience repulsion with the material of the surface of this capillary tube, the liquid molecules simply don't flush with this material of the capillary tube, and hence they experience a phenomena like this. The liquid molecules try to bind within the liquid body, and in the process, the liquid molecules closer to the surface of this capillary tube experience repulsion, and in the process, they experience a fall. Similar to a phenomena we observe here. The liquid particle, it does not flatten itself over this surface, rather it tries to retain its shape. Same kind of a phenomena is observed here. And during this interplay of forces, certain liquids experience a fall, while as certain liquids experience a rise. In this question, we have been asked about the rise of a liquid. So let us discuss the case of the rise of a liquid within the capillary tube. Now, so far we have understood that when a liquid is a wetting liquid, it would rise in a capillary tube, and if it is a non-wetting liquid, it would experience a fall. Now in this question, we have been asked to determine the rise. Therefore, it is understood that this liquid must be a wetting liquid. Secondly, let us try to understand the forces which exist in this system. A capillary tube is immersed in a liquid, the liquid rises, and an equilibrium position is obtained. This is an equilibrium position. In this equilibrium position, let us try to understand the forces in equilibrium. The most important force and the force behind the phenomena of capillary rise or fall is the surface tension, which is the attractive force which exists between the molecules of a liquid surface which makes the surface act like a stretched membrane. Now let us observe this surface, this liquid surface, very closely. The molecules in this liquid surface would be attracted towards the neighboring molecules. The molecules close to this glass surface would be attracted towards the molecules a little far away from this glass surface or the surface of the material of this capillary tube. Now, since this surface is in equilibrium, that means if an inward force is acting on the molecule just in contact with this capillary surface, there must be a force balancing this inward pull. Therefore, close to the surface, we have a force like this. This force can be broken down into two components in the horizontal and the vertical direction. Suppose if I denote this surface tension force as sigma, and if I denote this angle as theta, then the surface tension force can be resolved in two components. One is the sigma cos theta and the sigma sine theta. The vertical component of this force is sigma cos theta and the horizontal component of this force is sigma sine theta. This surface tension force is basically the force per unit length of the liquid surface. If we observe the surface from the top, it would look something like this. This is the plan or the top view of the surface of the liquid which has risen in the capillary tube. Here we have vertical forces of magnitude sigma cos theta. This force, which we have just understood here, towards the vertical sigma cos theta and sigma sine theta, which is the horizontal force. So we have the vertical forces sigma cos theta and the horizontal forces sigma sine theta play out like this if we look at this surface from the top. The horizontal forces are acting out in every possible direction. And if we resolve these forces over this circumference of the liquid surface, all these forces, sigma sine theta, throughout the circumference would cancel each other's pull, because these forces are acting in every possible direction, and hence there is no net force in the horizontal direction. But if we take a look at the vertical force on this surface, the vertical forces with the magnitude of sigma cos theta are acting over the entire circumference of this capillary tube. So these forces act in the vertical direction. Therefore, as we can observe, total vertical force is sigma cos theta, which is the surface tension or the force per unit length or per unit length over this circumference times forces sigma cos theta times the circumference. So this is the total vertical force, sigma cos theta times the circumference. Sigma is force or surface tension force per unit length, and we are taking the product of this vertical force over the entire circumference to add all these vertical forces acting all over the circumference of this capillary tube. Now, since this liquid which has risen in the capillary tube is stable, or it is in equilibrium, it's neither moving upwards nor it has a net downward movement. That means if there is a total vertical force acting upwards, there must be a vertical force, an equal vertical force acting downwards. So the possible force which is acting downwards is the weight of this liquid column. Let us recap a little bit. We immersed a capillary tube in the liquid, in a wetting liquid. The liquid in the container rose in this capillary tube and attained an equilibrium position. Now, we have learned that there is a total net upward force equal to sigma cos theta acting over the entire circumference of the capillary tube, or the entire circumference of the surface of the liquid which has risen in this capillary tube. And this total vertical force which is acting upwards is balanced by a total net downward force, which is possibly the weight of this liquid column which has risen in the capillary tube. So the weight of this liquid column, let us focus on this liquid column. I'm zooming in on this liquid column. It is a cylindrical column. And the weight of this liquid column is area of this surface times the height area times the height of this liquid column, which is basically the volume of this liquid column. So weight is volume times the unit weight, which in this question is given as gamma, weight per unit volume. So weight per unit volume times volume is the weight of this liquid column. So we have learned that since there is an upward force due to surface tension acting on this meniscus, which has a magnitude of sigma cos theta times 2 pi r, or the circumference, since this vertical force per unit length is acting all over the circumference. We have taken a product of these two to find out the total force which is acting in the vertically upward direction. And since this liquid which has risen in the capillary tube is in equilibrium there must be a total downward force which balances this total upward force. The total downward force is the weight of this liquid column. So therefore, this total upward force must be equal to this total downward force to maintain this equilibrium. So force upwards is equal to force downwards. Force upwards is sigma cos theta times the circumference. This must be equal to the volume of this liquid column times gamma, the unit volume of this liquid. So if we rearrange this equation, we get the rise of this liquid in the capillary tube, which is H equals two times the vertical component of surface tension, which is sigma cos theta, upon gamma times R. So this is the equation we need to remember for the rise of a liquid in capillary. Now let us take a look at the options given in this question. There is sigma upon 2r gamma, sigma upon r, 2 sigma upon gamma r, and gamma sigma upon 2r. So our answer looks similar to option C. We have found that rise is equal to 2 sigma cos theta upon gamma r. So this is the equation for the rise of a liquid in a capillary. Now you must have observed that there is no component of the angle mentioned in this question. Therefore, it can be assumed that the liquid in question, whose specific gravity is gamma, is basically water. Because when water is in contact with glass and the interface for both is air, the liquid completely flushes with the surface. That means theta here is 0 degrees and cos of 0 degrees is unity. Therefore, H, or the rise of a liquid or rise of water in a glass capillary tube, is 2 sigma upon gamma R, which is the option C. If this liquid would have been kerosene, theta in case of kerosene is 26 degrees. And if this liquid would have been mercury, theta in case of mercury is 130 degrees. That means if we put a droplet of kerosene on glass, it would flush something like this. Here we would have surface tension and an equal force causing kerosene to remain in equilibrium, and this force would be inclined at 26 degrees, or the surface of the kerosene in contact with glass makes an angle of 26 degrees. If this droplet was mercury, the cohesive forces in this case would be extremely dominant, and this angle, this tangential line drawn at the contact of mercury and glass would be close to 130 degrees inclined to this glass surface. And since there is no mention of theta in this question, so we could assume that this liquid in question could have been water, and hence the rise would be given as 2 sigma upon gamma r. Therefore, the right option is C. Now let us take a look at the question number 8. The question number 8 says that the intensity of pressure developed by surface tension of 0.05 newtons per meter in a droplet of water of diameter 0.05 millimeters. So we have a droplet of water with a diameter of 0.075 mm, and we need to determine the intensity of pressure developed by the surface tension. This surface tension. A droplet of water is spherical in shape due to the surface tension. That means all the molecules on the surface of this water droplet are attracted towards each other, which make it act like a stretched membrane. That is, the surface of the water droplet acts like a stretched membrane. Now, for the purpose of understanding, if we dissect this droplet of water into two, to understand the interplay of forces which are holding this droplet of water in this shape. Now, the molecules within the body of this droplet are attracted equally in all directions, and the molecules on the surface are attracted towards each other and towards the bulk of this water droplet, which make all the molecules in this water droplet cling to each other, and hence it assumes a spherical shape, with the molecules on the surface being attracted towards each other and making it act like a stretched membrane. Now, if we observe a molecule very close to the surface of this membrane, here, it would have been experiencing a force like this. Similarly, a molecule here on the surface would experience a force like this, and all other molecules within this part of the surface would experience an attractive force towards the other half of this droplet, like this. Now, the surface tension is the force per unit length, or it is the force which is acting over every unit of this circumference. The total force, or the total pull, or the net pull of the molecules on this water droplet surface would hence experience a force equal to the surface tension, that is the force of attraction on the molecules of the surface, times the circumference of this half. Surface tension, again, is the force acting per unit length, or the force acting per unit of this circumference. And therefore, the total force acting all over the circumference would be the unit force, or the force per unit of the circumference, times the entire circumference, or the length of this entire surface, which is the circumference. Therefore, total force will be 2 pi r times the surface tension, or the circumference times the surface tension. Now, since there is a force on one half of this water droplet acting something like this, therefore, there must be some kind of a force which is acting in an opposite direction. Because had there been a force like this surface tension force acting all over the circumference alone, this particle, or this half of the droplet, would have moved something like this. But this droplet is not experiencing any movement in itself, and therefore there must be a force which is holding this half of the water droplet in its position. And this force, which is acting in the direction of the force of this surface tension, is due to the inside pressure of this water droplet. That means there is an inside pressure in this water droplet which is balancing this force of surface tension. In this case, acting towards right. And the force which is caused by this inside pressure is acting towards left. The force due to surface tension in this case is acting towards right. Therefore, there must be a force acting towards left of this water droplet to maintain an equilibrium. Now, pressure is force acting per unit area, and therefore this inside force or the interior force acting towards left here in this water droplet is the inside pressure times the area. In this case of the water droplet, if I zoom in on the surface of this one half of the water droplet, there are surface tension forces and then there's a force acting per unit area. Suppose this is a unit area inside this water droplet. Every unit of this area of the water droplet is experiencing a force which we have denoted as the inside pressure. Therefore, this opposing interior force equals the inside pressure times the area. The area here in this water droplet is the area of this circle, which is the surface formed by dividing this water droplet into two. Therefore, this area is pi times radius squared. If I denote this force as the force acting towards left and the force or the total force due to surface tension as the force acting towards right, to maintain the equilibrium, force towards right is balanced by the force towards left. The force towards right is 2 pi r times the surface tension sigma equals the inside pressure times pi times radius squared. Therefore, the pressure in this water droplet is 2 times sigma, or the surface tension, upon the radius of this water droplet. So this is the formula we need to remember for determining the pressure inside a water droplet. This formula can be further modified as 2 sigma upon the half of diameter, which is 4 times the surface tension upon the diameter. Now let us plug in the values which have been given in the question number 8. The formula, as we now understand, is pressure inside a water droplet is 4 times the surface tension upon the diameter. Therefore, plugging in the values given in this question, sigma is 0.05 Newton per meter upon the diameter, which is 0.05 millimeters. Therefore, the pressure inside this water droplet is 4 times 0.075 newtons per meter times 0.075 times 10 to the power of -3 meters. Therefore, the inside pressure is 4 times 10 to the power 3 Newton per meter square, or 4000 newtons per meter square. So this is the answer for this question. But it looks like that the pressure has been given in centimeters squared. Therefore, we need to modify this solution a little bit. So the inside pressure is 4000 upon 1 meter is made by 100 centimeters. So the inside pressure is 4000 upon 10 to the power 4 Newton per centimeter squared, which makes inside pressure equal to 0.4 Newton per centimeter squared, which is the option C. Therefore, the intensity of pressure is 0.4 Newton per centimeter square. Thank you for watching.